We have been referring to mathematical models for quite some time. Now, in this video segment, I want to present to you one way in which models are classified. So mathematical models, one way to classify them is to look at them as linear and nonlinear models. So classification one is some models are linear, some models are nonlinear. Now let's take a look at the example that is given right here. So we have in this particular case 5 x variables and 1 y variable, and the x variables are related to y variables like what is shown there. So basically it represents a system where you have one output variable which is y, and the inlet variables are x1, x2, x3, x4 and x5. So there are 5 x variables that are seen to affect the y variable. As an example, in a distillation column, we could have y representing the distillate stream composition, x1 could be the reflex flow rate, x2 could be the amount of energy supplied in the reboiler, x3 can be the feed composition, x4 can be the feed temperature, and so on, right? So this is one example. And in this case, the modeler believes that the y variable, the output variable, is related to the input variable in this particular fashion, input variables rather. So x1, x2, x3, x4, x5 are the input variables like what I described for an example distillation column. Y is called the output variable. All right, so there are 6 variables in the system, x1, x2, x3, x4, x5 referring to the input variables and y referring to the output variables. So this model represents the belief of the modeler or the practitioner who says that the x1, x2, x3, x4 and x5 variables affect the output variable y in a linear sense, right? So that is why the modeler writes an expression of this type. So all the terms, right, enter linearly. So there is nothing like x4 squared or square root of x3 or log of x2 or x1 by x1 plus x2, things like that, right? So simply x1 affects y through this coefficient called a1. x2 is believed to affect y through this coefficient a2 and so on, right? So all the input variables enter the model in a linear sense. So this would be referred to as a linear model. So there are no terms like square root of x1 or x1 to the power of minus 0.2 or x1 by x1 plus x3 squared. So you have no terms like this. You don't have terms like exponential of x1, x3, things like that in the input, right? So all the input variables enter the model in a linear sense. So a model has a structure which reflects the belief of the modeler about the system she or he is working on. So if you write an equation like this, you say that I believe that the inputs affect the variables in this particular fashion, every input variable entering the model linearly. The parameters of this model are A1, A2, A3, A4 and A5. So every model has a structure, and with the model is associated parameters. And we find out A1, A2, A3, A4 and A5 using methods like linear regression or nonlinear regression. That means you try to find out from data what are the best values of A1, A2, A3, A4 and A5. Very much like in high school, you are given often, right, data on x and y variables, two variables, an input variable x and an output variable y, and then we are asked to find a model like this, right, mx plus c. So we would have done this in high school, for example. Find the best values of m and c, and there are some formulae given for us. So we kind of crunch numbers and then we say the best value of m, the slope of the line is this, and the intercept c is this. So you probably remember plots like this. So this is the y-axis, this is the x-axis. So you have data points. In this case, I'm showing, let's say, 4 samples of data shown here. And then what you do is you try to find out this line, right? The best line with a slope of m, and where it cuts the x-axis, that value is, that height is c. So this is the intercept. So this model is a linear model, right? Because the x variable on the right hand side enters as x, and then it has two parameters, the slope and the intercept. All right. So likewise, if you extend this idea that we did in high school to a system involving multiple variables, x variables, you will get a model of this type, right? Of course, you can have a term plus a naught if you like, where a naught plays the role of the intercept, right? So the model has a structure and it has parameters. If it has a linear structure like what you see here, life is easy. You can estimate the parameters a1, a2, a3, a4, a5, and a naught through something called linear regression. We will touch upon linear regression in this course, at least from a mathematical point of view, if not from a statistical point of view. All right, so we'll do that. Now, if you come to the second case, well, you see some nonlinearities, at least some nonlinear terms appearing there. For example, x1 squared is a nonlinear term, right? It's a quadratic term. X2 comes as exponential of x2. These terms look very linear, right? I mean, x3, x4, x5 are related to y just like x3, x4, x5, right? They are not squared, no square root, no logarithms, no sine of x3 or sine h of x4, hyperbolic sine. So nothing of that type. Simply these three terms are very simple linear terms, whereas you see non-linearities in variables x1 and x2. So this modeler believes that for his or her system, uh, x3, x4, x5 affect the output in a linear sense, whereas x1 squared affects y in a linear sense, right? So it's not x1 affecting y in a linear sense, it is x1 squared. That means the square of x1 is able to predict a good portion of y. That's what it means. And likewise for x2, exponential of x2, right? E to the power of x2 is a better predictor for y. So the person has written an equation reflecting his or her belief about the system that they are working on, right? So this is the belief of this person. Of course, one has to validate that belief, right? So you can have a belief, but then you should see whether the data supports it or not. So let's say this is the belief. Now, this model is nonlinear, but it is nonlinear in variables. It's not nonlinear in parameters. So for example, I can define a new variable x6, which is x1 squared. I can define a new variable called x7, which is equal to e to the power of x2. Then this model becomes y is equal to b1 x6 plus b2 x7 minus b3 x3 plus b4 x4 minus b5 x5. This looks very much like the first equation that we have, except that the parameters are now labeled b1, b2, etc. And some parameters are indicated with a minus sign, right? But once you replace exp of x2 with x7, all right, and x1 squared as x6, the second model becomes very much like the first model. So the second model is called as linear in parameters but non-linear in variables. You understand why it's called non-linear in variables, because you have x1 squared and e to the power of x2. They are non-linear transforms of x1 and x2 respectively. But it is linear in parameters because I can replace x1 squared by x6, and I can create a new variable x7 which is equal to e to the power of x2, and then I can get a model structure like this. Now I can estimate the model parameters b1, b2, b3, b4 and b5 using simple linear regression. All right, so the second model also does not pose a problem in estimating the parameters, etc. So the first model, you don't have to do anything. It is very linear as it starts. Therefore, you just say it's a linear model. That means it's linear in variables, it's linear in parameters. If you come up with the second model, you would say, well, that's non-linear in variables, but it is still linear in parameters. All right. Now, if you take the third model that is listed there, of course, you still see x1, x2, x3, x4, x5, the same variables, but this modeler believes that y does not depend linearly on x1 or x2 or x3 or x4 or x5. So this person says the relationship between x1, x2, x3, x4, x5 and y is this, right? By c2 e to the power of c3 x2 sine x3 plus c4 x4 x5. So this is the relationship that this person has proposed, right? And maybe he or she has proposed this model because they understand that the system is very nonlinear in behavior, right? So only a nonlinear model can explain how x1, x2, x3, x4, x5 affect y. So therefore, they have proposed a model of this type. And now you cannot do the transformation like we did in the second model, right? We cannot replace, e to the power of C3x2 because we do not know what C3 is now, right? We do not know that. And then there is a multiplication between exp of x2 and sine of x3, and here x4 and x5 multiply. Here x1 is divided by variables involving x2, x3, x4, x5, etc. So this is something that cannot be transformed to a linear form. So this model will be called nonlinear in both parameters and variables. All right. So presence of division, for example, right, where one input variable is divided by another input variable or combinations of other input variables, or when you have things like two variables x4, x5 multiplying each other, or exponential of x2 multiplying with sine of x3, right? So these kinds of multiplications of different x variables, they indicate nonlinearities. And what happens is models of this type, you cannot convert it into a linear kind of a form. So for this, to estimate C1, C2, C3, C4 from experimental data, you would have to resort to what is called nonlinear regression methods. All right, we will not touch out that too much in this course. If you have time, we will do it. But basically, you just have to understand that models can be linear or nonlinear. Now, most chemical processes are nonlinear, right? You can look at reaction kinetics, for example, you may be familiar with because you've done a course earlier on reaction kinetics, or you will be doing it together with this course. So basically, this is second order kinetics from even high school chemistry, right? So this is a second order reaction that takes place in a vessel or a pipe or whatever, and therefore in this particular case the rate of reaction of species A is K times Ca squared. So this Ca squared creates this nonlinear behavior in systems. Sometimes if you have a reaction like this A plus B going to C, then the rate of reaction of A can be K times Ca times Cb. So here you have a product of two variables, right? Two inlet concentrations, if you like, or two concentrations. So multiplication of two variables creates nonlinearity. In fact, this is quadratic nonlinearity. Ca squared is quadratic nonlinearity. If you have something like x3, x4 or Ca times Cb, this is called a bilinear term, bilinear, right? So it is a product of two variables. So this is called a bilinear term. It's not linear, but it is called as bilinear. So if you had x1, x2, x4, this would be called a trilinear system. All right. So bilinear systems are fairly common in chemical processes, as we shall see in some examples later. Okay, or you can find it out yourself, right? Once you understand this concept, if two variables multiply, right, then you would call that product term as a bilinear term. And of course, if you are looking at non-isothermal reactions, right, so you have this Arrhenius relationship, right? So you definitely have seen it in high school, Arrhenius relationship, where the reaction rate constant is not like a number like what you might imagine in isothermal systems, but this rate of reaction will depend on temperature, right? T. So K is given by this Arrhenius relationship as K naught, a frequency factor multiplied by e to the power of E by minus E by RT. So this is the activation energy, this is the gas constant, and T is the temperature of the system, right? So as the temperature changes, the value of K changes. And this relationship is nonlinear, as you can see, because K is equal to some constant multiplied by the exponential of, right? So this exponential term makes the dependency between t and k, it makes it a nonlinear relationship, right? So as t changes in a certain way, k will not change proportional to that, right? So if t changes linearly, k will not change linearly because of this exponential term. So that makes the relationship between T and K nonlinear. So therefore, as the temperature changes in the reactor, the value of K will change in a nonlinear fashion, right? In a fashion that makes use of this relationship there. and therefore K will change because T can change. If K changes, the rate of reaction changes, and that can mean a lot of things for the reaction chemistry and how much conversion is obtained in the reactor and so on. Yet another case is this flow head relationship, where it's like a simple tank, let's say, that stores water. The water is filled to a height h, and then the outflow from the tank, right? This is Q out, the flow out from the bottom of the tank. That is found to be of this type, right? It is typically kh to the power of n, right? If the flow is kind of steady and it's not turbulent, right? Then n will take a value 1. So the relationship will be Q out is equal to K times H for laminar flow. But when the flow is turbulent, for example, you will have n which is not equal to 1. That makes the relationship between the height of water in the tank and the flow here out of the tank to be non-linear, and that is given by this kind of a relationship. So in this case, n is shown to be equal to half. All right. So what happens is you will have many cases, as we shall point out later when we get to mathematical models. You will see that there are many bilinear terms. That itself makes the model non-linear. And in addition, reaction chemistry, like what you see here, uh, the dependency of reaction rate on temperature, or the dependency of the flow out of a tank on the height of liquid in the tank, all of them induce nonlinearities in systems. So nonlinear systems are more common. The world is nonlinear, except that we can say, because we are operating the process over a very narrow range around a certain steady state point, we can say that we are going to approximate it by a linear system. So linearization or a linear model is an idealization, right? Non-linearity is a norm. And that idealization is valid sometimes because we do not operate the process over a wide range. We operate the process over a very narrow range in which the nonlinear behavior doesn't show up as much. Therefore, we can assume that the systems are linear. So there are other cases. We will go into these models later, but you can see here, right? So let's take a continuous stirred tank reactor, CSTR. So it's a vessel, right? A cylindrical vessel typically, and there is a stirrer which kind of keeps the contents of the vessel homogeneous. So the job of the stirrer is to make sure that the concentration of all species is the same anywhere inside this vessel, right? So that's one thing. It is also there to ensure that the temperature is the same at this point, this point, this point, this point, whichever point you sample the temperature in the reactor vessel, the temperatures are the same, right? So basically it's an ideal system where you try to maintain homogeneous conditions within the reactor. So that's CSTR. And in a case where first order kinetics happens, right? The chemistry is first order reaction, A going to B, for example, where the volume V is constant. So this V dCA by dt, we'll look at this in detail later. This tells us the rate of accumulation of A in the reactor, right? So not all the reactant species A that comes into the reactor will go out or get converted into B. Some amount of A will remain in the vessel. So the rate of accumulation of A in the vessel is this term, right? We'll kind of do this later on, so don't worry. So this is what is called the rate of accumulation. Accumulation, right? This is rate of accumulation. So this is the inflow of A into the system, the rate at which A flows into the system, right? That comes through this feed term. That's the feed stream. So Q is the volumetric flow rate in, let's say, meter cube per minute. CAF is the concentration, which is going to be in moles of A per meter cube. Moles of A per meter cube. So if you multiply the two, you get moles of A per minute. So this is moles of A per minute coming into the reactor. This is the moles of A per minute that is leaving the reactor. That is the unconverted A, right? Not all of A is converted in the reactor vessel. There could be some unconverted A, right? So that depends on things like residence time and so on, the size of this vessel, stuff like that. So some A goes unconverted. That's the second term. And some A gets converted into B. So this is the reaction term, right? So this accounts for the amount of A lost because A is converted to B. And whenever things leave the vessel or whenever A is lost, you have a minus sign. And whenever A comes in, you have a plus sign. All right. So the point is this equation should make sense to us because this says this is the rate of accumulation of A in the vessel. This is the amount of A, the rate at which A comes into the vessel. This is the rate at which A leaves the vessel. This is the rate at which A gets converted into B within the vessel. So this is a balance, mass balance for species A. So what is important for us here is, please note this multiplication. Q is a variable, right? Q is a flow rate. CAF is the feed concentration of A. So one variable multiplies with another variable. So this leads to what is called bilinear terms, right? Which means this term is non-linear actually. But if you assume that the Q is constant, then this term becomes a linear term, because if Q is a constant, or if CAF is assumed to be constant, if one of them is assumed to be constant, then this term becomes a linear term. All right. So again, the same argument holds for this term as well. By itself, Q can change with time, CA can change with time. So Q times CA represents a bilinear term. But if one of them is constant, then you can say that's a linear term. If both are constant, then it will become a constant term. All right. So these bilinearities are quite common in chemical processes because you always multiply quantity with quality. So Q is quantity, CAF is quality. So product of quantity and quality is always very important everywhere, anywhere in life. Our success is kind of created, whatever success means, right? That's created by both quantity and quality. Both should be there. Okay, that's what it is. Now, the second equation that you see there is about a simple, tank that mixes two streams of hot water and delivers a stream outside, right? So this is a stirred tank heater, if you like. So CSH, stirred tank heater, continuous stirred tank heater, where two streams are brought in, they are mixed, and the product is sent out. So this is the rate of accumulation of energy within the vessel. This is the amount of energy coming into the vessel. This represents the amount of energy that enters through stream 2. This is entering through stream 1. This is like, if you put them together, it is like minus Q1 plus Q2 times T. So basically, this tells us how much energy leaves the vessel through the product stream. So inflow, two terms, so they come with a plus sign and a plus sign. So two inflows bring in energy into the system. There is this one outflow with a flow rate of Q1 plus Q2 that takes out energy from the system. And the imbalance between the inflow of energy and the outflow of energy is the accumulation of energy. Okay, so that's the meaning of this equation. Now, again, Q1 is a variable, T1 is a variable, Q2 is a variable, T2 is a variable. So when these two variables multiply, Q1 multiplies with T1, you get a nonlinear, bilinear term, in fact, right? Same with Q2 and T2, same with Q1 times T and Q2 times T. So the bilinear terms are very, very common in chemical processes. So I will stop this video segment here and continue with our discussion of linear and nonlinear models in another video segment. Thank you.